Michaela, today and next lesson, we're going to learn the fundamental rules for solving circuits. And any of you that go on to look at further electronics, Nick, it's all going to be based on this. So you don't want to be looking at your phone or anything foolish like that. Instead, what I like about Kirchhoff's laws is there's an algebraic version of this, and in fact, that's how I used to teach it. When I first started teaching, we solved all of these through systems of equations. And then another physics colleague of mine gave me my ski hill analogy. And so we're going to go skiing on a nice, hot, summerish day. There are two main laws for solving circuits. There's Kirchhoff's current law, which I often abbreviate as KCL, and then there's his voltage law. Kirchhoff's current law is basically a conservation of charge. Electrons can't vanish magically. They're stuck inside the circuit. So here's what it says. It states that at any junction between wires, current flow splits or combines and continues to flow downhill. When the current splits or combines, no charge is lost, so that the total flow into a junction equals the total flow out of a junction. Don't underline anything there. That's very, very confusing. It's much easier to think about mathematically, and in particular, when we look at a circuit. Here's really what it says. The total current in has to equal the total current out. This is not going to be on your formula sheet. You'll do a few of these and it'll just become second nature to you. In terms of my ski hill analogy, Drake, it means that skiers can't vanish. Once they go up the chairlift, they're not allowed to disappear on the mountain. Then we have to call it the North Shore Search and Rescue. Not allowed to do that. Okay? So, suppose we have 2 amps of current flowing in here and 1 amp of current flowing in here, and then they're going to go this way. How many amps must exit that junction? 3. That's Kirchhoff's law for current. Current in equals current out. And this is why Nevada typically, as soon as I have a current, if they haven't already put arrows, a circuit, if they haven't already put arrows on it, I always label arrows which way is downhill, because that's which way we're going to ski. So here's the first one, example 1. Let me zoom in a little bit. It says this: find the unknown currents. So the first thing that I find is the battery. That's our chairlift. That's our source of energy. That's what's increasing the voltage, the height of the charges. And so the first thing that I would do is I would say charges flow downhill from positive to negative. Electrons flow the other way. But again, Kyle, this is why we prefer to think about positive charges. It's much easier to wrap my brain around. Okay. How many amps left the current? If I can find the amount of amps that have left the current, the question falls apart and I'm done. Well, how many amps are right here? How many amps must be right here? How many skiers must be right here? 1.75 amps, 1.75 amps. So you know how many amps left the current? 1.75 amps. How many amps are right going through this resistor? 1.75 amps. How many amps right here? How many amps right here? How many amps must be right here? 1.75 amps. Put units always, because you'll be putting a bunch of numbers on your circuits, and if you don't put units, you'll forget which one was the resistance and which one was the current and which one was the voltage. Okay. Downhill is right there. How many amps total are in this circuit? How many amps are leaving the chairlift? 3. Okay. So 3 amps go this way, and then I guess 0.8 amps went this way. How many amps must have gone this way? Do the math in your head. 2.2. Let's continue skiing down this run. So they ski along a pathway, a nice level pathway, and then here's the ski hill. The current, the electrons, the charges go through the ski hill. Which way is the current flowing right here? To the left or to the right? Must be going to the left. And how many amps? Well, how many amps right here? 2.2. How many amps right here? 2.2. How many amps right here? How many amps right here? And then I notice I have 2 junctions combining. How many amps were coming down this path? How many amps coming in this way? How many amps here? 3, and I also could have figured that out because if the total leaving the chairlift is 3, the total entering the chairlift the battery has to be 3 as well. So you'll often find, James, there are many ways to get the answer. Oh, what direction is the current flowing right there, to the left or to the right? That, in a nutshell, is Kirchhoff's law. All I can do is give you more junctions and more paths. Kirchhoff's law for current. Yep. Got to zoom out a little bit. Let's kick it up a notch. I always enjoy solving circuits. I find these little addictive brain teasers, brain puzzles. This is like a jigsaw puzzle to me, and I enjoy, solving them. Come here, computer. There we go. It says, show the direction of each current and find the unknown currents. This is getting closer to what you might deal with, except even now this is too easy. But the first thing I always do is I say, okay, find the battery, downhill is that way. And now let's walk through all of our ski runs. Kayla, up here we're going to the right. Downhill is to the right. And I guess downhill on that middle junction is down the page. That's downhill, that's downhill. I guess on the far right, that's downhill. And then on the bottom junction, to the left is downhill, to the left is downhill, to the left is downhill. This is the direction that I'm going to trace my eyes. When I'm solving a circuit, I always want to find, if I can, the total current in the circuit. How many amps are leaving the battery? How many amps are leaving the battery? They didn't tell me. Or did they? What, Connor? 13, yes? Because if somehow right here I have 5 going this way and 8 going this way, right here I must have had 13 amps coming in. You okay with that, Robbie? Basically what happened is here, the skiers shook hands and said, okay, 8 of you are going to go this way, 5 of you are going to go this way. Let's follow these 5 skiers. They come to another fork in the trail. They shake hands. How many amps went this way? Down the bottom one there? 2. How many amps, Nick, must have gone this way? Has to. Yep. How about this little bottom current right here? Got to be 3 because there's no other junctions, so all the skiers are still skiing in a group, those 3 skiers. They meet up again right here. How many amps must be right here, Nick?
5.
Yep. How many amps must be right here?
50.
Yep. That's how amperage in a direct current circuit splits up and rejoins. The total current doesn't change. Well, we'll talk about how the resistors will change how much current you're getting out of the battery, but for now, I'm just telling you how much current we're getting out of the battery. Let's kick it up a notch. Okay, downhill is that way from the positive. Downhill is that way. And then it looks like in these 3 resistors, that's downhill, that's downhill, that's downhill. They meet up, that's downhill in our ski circuit. That's downhill, that's downhill, that's downhill, and then they rejoin. Do I know how many amps grand total are in this circuit? How'd you get that so fast? Oh, because all the skiers are rejoined and they all go through this resistor. If I know there's 5 amps there, and that's everybody joined together, must have been 5 amps leaving my battery. How many amps must be in this right-hand resistor? 2.5? So I still have my total of 5. So again, Drake, you can think about it. A bunch of 5 skiers met here and they shook hands. Now my analogy breaks down because what's half a skier? But 0.5 skiers went this way. 2 amps went this way. That left 2.5 amps to go this way. And then they're going to meet up right there. 5 amps. Oh, Drake, how many amps must have gone through this path? How many amps right here? How many amps went this way? Yes. Okay, don't make that, that's a silly mistake now. See how it all fits together? Okay. Generally, if I can find the current in a circuit, everything else falls apart. One more. It's a nice sunny day. Nevada, you want to go skiing? Let's go skiing. First thing, Nevada, we're going to label downhill. So downhill is that way, and I guess it's going to go this way, this way, this way, this way. I put a few arrows on, and that tells me also kind of how I'm going to move my eyes around so I don't accidentally end up skiing uphill. Nevada, do I know how many amps are leaving the chairlift? How many? Yes, okay. Total current is, say it again. The fact that I know that, I'm telling you the question's going to fall apart. That's my benchmark when I get to really nasty circuits is as soon as I have the total current, it's going to fall apart. I'm going to ski the rest of the question through. How many amps right here? How many amps went this way? So how many amps went this way? Yep. How about how many amps are in this resistor right here? How many amps are in this resistor right here? Yep. How many amps are in this section of wire right here? If you put an ammeter, how many amps would you measure right there? 3.5. How many amps would we measure if we put an ammeter right here? And we get to the bottom of the chairlift, Nevada, you and I shake hands, and we say, good run. Yeah, turn the page. The amount of flow along a particular path from a junction depends on the resistance of that path. Higher resistance means you're going to get less current. There are some tricks you can memorize as shortcuts. The only one that's kind of necessary and kind of makes sense is this next one. Suppose the resistance of each path is the same. So we have 6 amps and there's 2 identical ski hills. What would make sense for how the current might split up if both ski hills are identical? 3 and 3. That's one I may pull out once in a while. I may once in a while not give you enough numbers to solve the circuit, but I may say, hey, these 3, if there was 3 identical resistors, it would go 2, 2, and 2. You can take it further than that. So if one path has more resistance, then what can we say about the splitting of the current? Small resistor versus big resistor. I1 is going to be bigger than I2. Small resistor, you can think a wider ski run, you can fit more skiers on it. Big resistor, high resistance, tough to go through. You can think, oh, it's a narrow trail, you can only fit a couple of skiers on there. I use that once in a while as a bit of a built-in error check. Do my numbers make sense? For what it's worth, and this part you don't need to memorize, it can be used as a shortcut. If the resistors are simple ratios of each other, we can relate the currents via the same ratios. For example, here, one resistor is R, the other resistor is 2R. This is twice as big. It's going to have half the current. So how can you divide 6 amps up so that this has half the current of that one? Yeah? Yes. I'll be honest, Duncan, I can't recall too many times where I've had to use that. I can recall a couple of times where I used it as a shortcut because I was lazy and didn't have a calculator handy. Okay. Voltage. So Kirchhoff's current law comes out of conservation of charge. Electrons can't vanish, and since current is the number of electrons per second, current can't vanish. Voltage comes out of the law of conservation of energy. Kirchhoff's voltage law, I'll sometimes abbreviate that as KVL, says this: as charges flow around the circuit, they experience voltage gains and voltage drops. For every path around the circuit, the voltage gain equals the voltage loss. Say, what? Here's what we really say. The sum of all the voltage gains has to equal the sum of all the voltage loss. I don't even like that one. In fact, and the earlier box where I said the total current in equals total current, I don't memorize that. I memorize skiers can't vanish, and that makes more intuitive sense to me. What did I say voltage was very similar to as our gravity analogy? Begins with letter H. Height. Here's what it really means. If you go skiing and you end up back where you started from, you better be at the same height you started from. Any height you gained, you had to have lost. And that's for anywhere we decide to start measuring you in the mountain. If we start measuring you partway through a ski run and you lose height, I'm telling you, if you're going to get back to where I started measuring you, you have to gain exactly that same amount of height and then lose some of that height to get back there. Gonna make it, Drake? You look a little weary. Uh-huh. So, in the ski hill analogy, here's what it says. If the chairlift takes you to the top of the mountain, if you get to the bottom of the mountain, you better lose all that voltage. So if this, for example, was an 8-volt battery, and if this is 5 volts, how many volts must I lose going through the next resistor? I have to have lost 3 volts. Here we go. Kayla, let's go skiing. You ready? Kayla, my angel, how many volts are we gaining from the battery? Oh, stop. First thing, label current. That way, that way, that way. So now we know which way is downhill. Kayla, how many volts are we gaining from the battery? So right now, the height is 20 volts. Remember, the resistors are the ski hills. So our height right here is 20 volts. Our height right here is 20. We're going to assume the paths that lead to the resistors are dead level. So what's my height still right here? Yep. How many volts do I lose going through this first ski hill, Kayla? Leaving how many volts? Start with 20, I lose 8. What's left? You can use a calculator if you need to, or you can do it in your head. 12. With me so far? So how high are we right here, Kayla? Good. Now, ready? How high must we be when we get to the bottom of the chairlift? So how high must I be right there? Also, what must I have lost there? Yep. That's Kirchhoff's law for voltage. And if you were a glutton for punishment, you could have started your measurements like right here and gone all the way around. I typically try and start from the top of the chairlift because it's way easier for me to think, well, what's the total voltage, total height? Make sure I lose it in any ski run. Thank you for skiing with me. Riley, let's kick it up a notch. You ready, Riley? How many? Oh, first of all, put the current in. That way, that way. I guess that's downhill, that's downhill, that's downhill, that's downhill. Now I know which way I'm going to move my eyes and ski. Riley, how many volts high is this battery? So voltage right here is? Yep. It looks like right here we split up. Let's ski down the middle run first. So still 10 volts high. I notice when I go down this ski run, I can get to the ground without going down another hill. So what must my voltage be right there at the bottom of the hill? And what must my voltage loss be going through the hill? Yep. What about this right-hand hill? How high am I right here still? Yep. What must I lose going through this hill? Otherwise, there's no way I could get to ground level there. So you can imagine, I guess we all, the skiers, the voltage is not current, whatever amps are flowing through this circuit, they came to a fork, they split up, and they all went down one ski hill and then met up at the bottom. They lost the same voltage going through each hill. Turn the page. Tori, let's go skiing. Label the current that way, that way, that way, that way, that way. Tori, how many volts are we starting out with? Okay, so what's the voltage here? Yep. And then I guess all the skiers go through this hill. So how many volts do we have right here? So how high are we right here? Yep, let's go down this middle run together, you and I. It looks like we go down one more hill, and how high does that get us to? So what must the voltage drop be through that hill? Gotta be. And how many volts high are we right here? Yep. And this also gets us to 0. What must the voltage drop be here? Yep. By the way, in a few seconds, I'm going to stop labeling everything, and we're just going to say all we're going to label are the resistors, the drops. That's all we really care about. But we'll do one more. James, ready to go skiing? Yeah, sit up. Oh, sorry, my bad. James, how many volts is this battery supplying? How high is this chairlift? Oh, stop. Let's label the current. That way, that way, that way, that way, that way. So how many volts right here, James? Yes. How many volts do I lose going through this hill? Leaving? So both of these are 45 high. Let's go down the middle hill. How many volts do we lose going through this hill? What do we start with? Leaving? Whatever 45 take away 18 is. 45 take away 20 would be 25, 27? Double check me. Yes? And if you need to use a calculator, go ahead. Although this is where my nerd kicks in and I try and do these in my head. How many volts high right here? Let's keep going. Let's keep going. What's my voltage right here as I hit this hill? Still. Yep. How many volts must I lose going through this hill? And here's your hint. This one, sorry. This one right here. And here's your hint. How high are we there? I have to have lost 27 volts. Otherwise, it's impossible. Really, what we're saying is otherwise, you violated the law of conservation of energy. You gained or you lost some energy that wasn't part of the system. Let's ski the other run. How high are we right here? What do I lose going through here? Leaving. Good. Ooh. Well, wait. How high are we right here? Well, let's backtrack. How high are we right here? 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 So what must I have lost going through that hill? How high was that hill? How many volts did that resistor use? Yep. See? Thanks for skiing with me. There are two useful conclusions to draw from Kirchhoff's voltage law. Number one, for any complete loop around the circuit, the voltage drop equals the voltage gains. But also, number two, no matter which way you go between two locations, the drop must be the same. In other words, if from here to here, going this way, I lost 18 volts, I had to have lost a total of 18 volts going that way. And sure enough, 10 volts and 8 volts is 18 volts. I always tell people, if you shake hands, split up, and then meet up, you have to be starting at the same height and ending at the same height, so you must have gone through the same voltage. My friend who typed these notes included this. He said, to see the voltage relationships, it's sometimes helpful at first to redraw the circuit so that all of the resistors are pointing downhill. For example, if you look at example 5A, which was this one here, you could redraw it like that. So here's the chairlift. Everybody goes through this hill. Here's the chairlift. Everybody goes through that hill. And then here's the junction where we split up. Here's the junction where we split up. And it looks like everyone meets up right there. It looks like everyone meets up right there. I'm not wild about that, but if you find that more helpful, go ahead. I encourage you, though, just put arrows in and get used to moving your eyes around. It's less work. Same idea, 5B, the one that James and I did, could be redrawn as follows. So again, here's your great big chairlift. Here's your great big chairlift. Everybody goes through that resistor. Everybody goes through that hill. We split up. Some people go this way. Some people go that way. Some people go this way. Some people go that way. But then we all meet up. We all meet up at the bottom. Example 6 says, write equations relating the voltage drops in the above circuits. I'm going to pass, and I'm going to go straight to example 7. And again, here's a couple of little shortcuts that you can use that aren't all that necessary. But for what it's worth, if we have two identical resistors along a path, what can be said about the voltage drops? Well, ready? What can you tell me about the current in each of these resistors? Different or the same? Gotta be, because the total current is here, total current is here, total current is here. So you ready? I is the same for both. And the question has told me that R is the same for both. So what can you tell me about the voltage? Hey, it'd be cool if there's an equation that had a V, an I, and an R in it. There is. Ohm's law. So, if V equals I times R, then let's call this V1, let's call this V2. I guess V1 and V2 are the same. In fact, in this case, they must each be 15 volts, otherwise that's impossible. You're gaining 30 volts, going through two identical resistors, 15 volts apiece. What can we say about the division of voltage if the resistors are not the same? Well, again, same current. That's Kirchhoff's current law, right? Total current leaves here and there's no junctions. So 3 amps or 5 amps or whatever is going through each of them. So same current. And V equals I times R. Which one has a bigger R? Top one. V1 is going to be larger than V2. A bigger resistor will have a larger voltage. I really don't use that last one, this one here, very often. Oh, and the one I also almost never use, but okay, I'm a nerd. They are simple ratios of each other. We can relate the voltage drops via the same ratios. So if I know that this resistance is twice as big as this resistance, the voltages are also going to be in a 2-to-1 ratio, and the bigger voltage goes with the bigger resistance. How can I divide 30 volts up into a 2-to-1 ratio? I can't think of a time where I had to use that to solve something. I've used it as a shortcut. Although it's helpful at first to label the voltages at each point in the circuit, it's desirable at this point to only label the gains and drops. This, example 8 and following, is much more likely what you're going to get on your test, circuits to solve. And what I'd like you to do above this, I'd like you to write our two main equations. We have this, V equals I times R, and we have power equals VI. And what you're going to hear me say over and over and over again is, if I know any two, I know all four at any point in the circuit. We're going to solve a circuit. You might want a calculator handy, although you may be able to do some of these in your head. So example 8 says, find the unknown voltage drops, currents, resistances. I'm going to say, and power. We're going to see how many watts each of these. Let's pretend these are all light bulbs. We'll see how many watts each of these light bulbs is. Here we go. First thing I do is I start at the circuit, and at the battery, and I label which way is downhill. Also, that gets me writing stuff on here. Andy, my juices are flowing. I'm doing good. Then I always want to find total current first. Andy, do we know the total current leaving this battery? Let's see. First of all, I look. Did they tell me right here? Say no. Let's ski. Do I know the current right there? How many amps? How many amps right here? How many amps right here? How many amps right here? How many amps are leaving the battery? This question's going to fall apart. In this resistor, what's the resistance? Well, I know the voltage, 6. I know the current, 4. V equals I times R. Get the R by itself in your head, please. R equals what over what? So V, 6 divided by 4. Anyone, anyone, anyone? Sorry? This must have a resistance of 1.5 ohms. I didn't write any work, and I won't make you show me that work, but I will say what I'll look for is that thing labeled on the circuit. That's part of my marking scheme. And just for giggles, how many watts is this? Power is V times I, 6 times 4 in your head, no calculator required. This is a 24-watt bulb. You okay with that, Andy? We've analyzed that part. Let's keep going. And it's all about the currents first, if I can get the currents first. How many amps right here? We split up. How many amps went this way? How many amps went this way? Good. Are there any more currents to fill in? So you know. So now let's start skiing. Okay, we're going to go on ski runs. Now we're looking at voltages. How high? How many volts? What do I lose going through here? Leaving. Let's go down this one. Here's one hill. Did that get me down to the bottom? How many volts must I have lost going through there? So what's the resistance? So did you, by the way, you wrote V equals I times R at the top of your page? And you're good enough now, so R equals, is it V over I? Right? So 12 divided by 3? Yep. It's a 4 ohm resistor. Oh, how many watts is this bulb? Andy, my friend. You wrote it down at the top of your page, yes? Power equal, did you, please tell me. Yeah. They're both there.
36.
Yeah. You will end up memorizing those two because you get sick of looking them up, and it's worth memorizing those two. Everything else is redundant. Okay, Andy, let's go back. We'll ski the other run. Ready? So now we're going to follow this path. Don't write that down, but we're going to follow that. Look up that path. Okay? How many volts? Did it lose? Leaving? One hill here? Okay. How many volts must this hill be? What's the resistance in your head, please? 12 ohms. How many watts of power? Also 12 watts. I'll tell you what I would do. I would not give you a question like this and say solve. I would say, which bulb is brightest? And I'll ask you, which bulb is brightest? Yeah, middle one. And initially that seems like such an intimidating question, but can you see even Andy could do it all in his head? Right? But if you don't know Kirchhoff's laws, you're, what? But if you wrap your brain around Kirchhoff's laws, this all falls apart. And it's skiing. Kind of fun. I love solving these things. Rebecca, ready to go skiing? Let's go skiing. So first thing I always do, current goes that way, that way, that way, that way, that way. That way. Okay. If I can, I'd love to find total current. Did they tell me how many amps are coming out of here? Not blatantly. Do I know how many amps? Because the total current is what's going through there. Do I know that? No. How many amps went this way? How many amps went this way? How many amps must have been coming in? How many amps must be right there? How many amps must be coming right there? Did they tell me total current? Yeah, they did. Not blatantly. Do I now know total current? This question's going to fall apart, I'm telling you. All right. What's the resistance of that first bulb? This one you'll probably need a calculator for. Whatever 21 divided by 2.5 is. Drake, you okay with how we're finding that, right? V equals I times R, so R equals V over I. What'd you get? 8.4? Ohms. And just for giggles, how many watts? 21 times 2.5 is going to be 42 plus 11.5. It's going to be 52.5. No? Yes? Yes? Okay. Let's keep skiing. Currents first. How many amps right here? Oh, you know what? They gave us all the currents. So now we're going to ski runs looking at voltages. There's that hill, and then there's that run. All righty. Let's do this first one. How many volts do we have?
35.
What do we lose?
21.
Leaving? 14?
14.
Yeah. Did that get us to the ground? How many volts?
14.
Do I know two things now in this resistor? Then I know four things. I can tell you the resistance. I can tell you the power. As soon as I know two, I know four. Resistance, oh, I can do that in my head. 14 divided by 1, 14 ohms, yes? Oh, power, I can do that in my head. 14 times 1, 14 watts. Yes? Let's ski the other one. Now, ready? Show you a shortcut. We shook hands right here and split up, and we met up. How many volts did we go through here?
14.
How many volts in total must we go through here? Got to lose 14. Otherwise, there's no way we can start at the same height and end at the same height. This has to be 14 volts. I don't need to go through the whole circuit. I can start to look at little mini runs. Do I know two things in that right-hand resistor? Then I know four things. Find the power, find the resistance. Power is going to be 14 times 1.5, 21. 14 divided by 1.5, that's going to give me a yuckier repeating decimal of some type. What do you get? It is 21 watts, isn't it? Is power not 21 watts? Yes? What's the resistance? 9.3? 14 divided by 1.5? 9.3? Oh, 9.3 repeating, yes? Okay. It's going. Sure, it's a repeating decimal. And again, I would be okay you showing me that much work. You don't need to write down that you went 14 divided by 1.5 equals. But label it somewhere. I'm okay with that. Shade, want to go skiing? Let's go skiing. Okay. Did they tell me total current? No. Is there any way I can find the total current right now? No. But I always try that first. If that doesn't work, I go skiing. Let's try this ski run here. Oh, you know what I should have done first, though? I should have labeled the current direction. Downhill, 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 downhill. Okay. How many volts, Sinead? I don't know how many I lose here. How many volts do I lose here? Did that get me to the ground? Ding, ding, ding. Now I know how many volts I lose here. How many volts must I lose here? Yep. How many volts must I lose here? Connor. That was a long blink, Robbie. You gonna make it? Yeah! Okay. Good. Hey, hey, hey. I know two things. I know two things. I now know four things. So I know two things over here. How many amps must be going through this? So now use V equals I times R, but get the I by itself. I think it's V over R. 7 amps? How many amps in total in this circuit then? Sinead, how many amps went this way? How many amps went this way? How many amps right there? Right there. Right there. Ding, ding, ding. Question's going to fall apart. Now I'm going to find four things on everything. So I'm going to now analyze every single resistor and find all four things. R equals 5 divided by 8. That's 0.625, yeah? And power is going to be 40 watts. V times I. R is going to be 35 ohms, 35 divided by 1, yes? And power is going to be 35 watts, V times I. Here, all I need is power, and that's going to be 35 times 7, 210 plus 245? Okay? Here would be an advanced question. I could give you this circuit and I could say, which one of these is probably not a light bulb? Okay, that right-hand one, I don't know of too many 245 watt bulbs. Even those heating bulbs are typically only around 200 watts. This is an appliance of some type. Yeah. Quick look of money. How many more am I doing here? A couple more and we're done. Good. Liam, you want to go skiing? You guys are all looking so awake this morning. So, label downhill. This way, this way, this way, this way, this way. Did they tell me the height of the mountain, Liam? Did they tell me the chairlift, the battery? Yep, okay. And I always look first. Did they tell me total current? Where? Oh. So, how many amps went this way? 5. How many amps went this way? How'd you get that? Okay, we can calculate it. If I know 2, I know 4. So I know 3 amps, and now this question's going to fall apart. Liam, how many amps went this way? How many amps are in the bottom resistor? Okay. Now let's look for voltages. Well, there's a bit of a problem here. First of all, there's 2 ski runs. There's that one, and there's that one. Let's see. Starting here with 70, I don't know. I lose 15. I don't. Oh, wait a minute. I know 2 things here, then I must know the voltage drop there. How many volts do I lose there, Liam? Yeah. Oh, great. Now I got a complete run. How high, Liam, my friend? What do I lose here? Don't know, but then I lose 15, I lose 20, and that gets me to the ground. How many volts must I lose here? $35. 35? Cool. How many volts must I lose over here? Because if we can split up and meet up, if this hill is 15 high, this hill here better be 15 high. I think I know 2 things on every single resistor. Now I can find all 4. The resistance is going to be V over R. This is a 7 ohm resistor. And the power is going to be 35 times 5, which is going to be 150 plus 25. So 175? Yeah? Watts. Here, the power loss going through here is V times I, 45 watts. Here, the resistor is V over R at 7.5 ohms, and the power loss going through there is 30 watts. And the power loss going through here is 100 watts. Is that right? Yeah. There's a bit of a typo glitch here. This line should really be right there, but it's an old diagram and I can't fix it. I don't have the original anymore. But I think what I'm saying here, Robbie, is downhill is this way, this way, this way, this way, this way, this way. Connor M., want to go skiing? Let's go skiing. Connor, did they tell me total current? Yes. Sort of. In this resistor, do I know 2 things? Then I know current. And why is that so handy? Because that's going to be the total current, and I'm telling you, the question's going to fall apart. How many amps are going through this resistor? What's the total current going through this circuit? 4 amps. 4 amps. Do I know how many amps went this way? Or how? No, I don't. So now I've exhausted what I can currently do, no pun intended, with Kirchhoff's current law. Let's move on to the voltage law. Let's ski. How many volts is this battery? What do we lose going through here? Leaving?
14. 24.
Did that get me down to the bottom? How many volts must I lose going through this single resistor?
24.
Yeah. Look up. Connor, how many volts from here to here? How many volts going through here? 24. That doesn't mean each one of these is going to be 24. It's going to, oh, well, wait a minute. How many volts right there? How many volts must this one lost then? Yes. That's Kirchhoff's voltage law and its little shortcuts that you can cleverly use. I notice I know two things right here. How many amps going through this branch? It's going to be 24 divided by 10, which you can probably do in your head. There you go. How many amps were there in this circuit grand total? So how many amps went up the middle? How many amps are left to go this way? Yep. Oh, and Connor, if there's 1.6 amps going down this hill, how many amps are going down this hill? Yep. And now, let's fill in the blanks. Whatever 14 divided by 1.6 is. 8.75 ohms. And what's the resistance of this top one? Whatever 10 divided by 1.6 is. 6.25? And I could find the power V times in any of them. I'll skip that step. Light bulb questions are a good way to test your understanding of Kirchhoff's laws because the brightness of a bulb is related to its power. And that's why I started already mentioning those, which really means it's related to its V times I. Example 9. If the bulbs below are identical, same resistance, which bulb is brighter? Well, what can you tell me? How many volts do we lose going through this bulb? Must lose 10 because the current goes that way. How many volts do we lose going through bulb B? Must lose 10 volts because you can also go that way. If we have the same resistance and the same voltage, what can you tell me about the current here and here? Come on. So, same I, same V. Yes? What can you tell me about the power? So, same brightness. Gotta be. What if I hook two identical bulbs up like this? Which bulb is brighter? Let's find out. R is the same for both because they're the identical bulbs. What can you tell me about the current going through each of these? What can you tell me about the voltage then going through each of these? If you have the same I and the same R, what does V equal? Because it's I times R. In fact, I can even be more specific. 5 volts and 5 volts because they told me I got 10 volts to play with. So if you have the same voltage and you have the same current, what? Same argument as before. Same V, same I, same power, same brightness. What's your homework? Practice a bunch of these. You got to get good at this. You can now handle number 1. And again, try and do these, show your work, but if you can do these all on your calculator and just filling in the numbers, I would probably at the top of the page write V equals I times R and P equals V over I, P equals V times I, and from that I can derive everything else. So number 1, number 2, number 3, Number 4. 5 is tricky. 6 is good. 7 is good. 8 is good. 9 is good. 10 is good. 11 is good. Oh, I love these things. 12 is good. I'll skip 13 because I'm nice. 14. Nah. There you go.